Physics is the essence of the way the physical universe works. We live in the physical universe. Basic everyday processes involve the fundamental laws of physics. Physics is the fundamental science. The laws of physics underlying everything that goes on in the universe. Physics is for everyone because physics is the essence of what most of us do. In fact, what all of us do all the time. So physics is something that describes the entire physical universe, from the smallest subatomic particles, the quarks and the electrons, to the grand scale of the entire universe and how it seems to be evolving. Modern physics was developed in the 20th century. It arose out of slight discrepancies between classical physics and the reality of the physical world that were noticed in the second half of the 19th century. At the fundamental scales, the universe is grainy in a sense. It's built up of little discrete parts. It isn't continuously subdividable. That was known before the 20th century. What's new about quantum physics is it quantizes or makes discrete not only matter, but it also quantizes energy. Quantum physics tells us that the world at the most fundamental level consists of discrete little bundles of stuff. Bundles of matter, bundles of energy. The universe, including the energy, is not infinitely subdividable, but comes in discrete little hunks.
Louis de Broglie put forward a simple idea that significantly advanced the understanding of the extremely tiny. De Broglie suggested that matter particles could sometimes act like waves, and when this idea was applied to Bohr's atom, it answered many questions. The more precisely the position is determined, the less precisely the momentum is known. It was the insight necessary to understand how an object can be both a particle and a wave. This single statement led to the understanding that subatomic particles can disappear and reappear in another place. And they can do this without existing in the intervening space. When an electron is trapped inside an atom, the places it can disappear and reappear include specific locations around the nucleus. Basic particles can also be in more than one place at a time, if the time is brief enough. An electron can travel along all possible paths simultaneously. The particles jumping around coming into and out of existence. Particles can appear out of the nothingness of space, exist for an extremely brief instant, and then disappear. All this jumping around makes particle description so inexact, but then existence itself is inexact at these tiny scales. What is it that is waving when a particle is described as a wave? Existence is waving. The wave is a map of the particle's existence, and as the wave changes, the particle changes as well. Schrödinger's equation manages to account not only for the hydrogen atom, but it describes nothing less than all the atoms in the universe. The solution to Schrödinger's equation, called the wave function, is a fantastically accurate description of the real world. And when two particles interact, their wave functions become entangled. When does this wave function collapse? It's possible that for an extended period of time, seconds, even minutes, our electron can effectively be in both places at once. One way to think of this is that the electron has a flow of time that depends only on the next interaction. And once that happens, time has moved forward.
Quantum mechanics was so radical a theory that completely shattered all previous ways of looking at the universe.
There are some very queer phenomena in quantum physics that don't exist in classical physics. In the classical world, everything goes like clockwork. If you know where everything starts and how it's moving, you can predict where everything's going to end up. Quantum mechanics has this concept of uncertainty built in.
At the fundamental level, the laws that govern the universe are not even deterministic.
Quantum mechanics is based on statistical thinking. Randomness, a certain degree of unpredictability.
Quantum mechanics gives us fundamental, unavoidable indeterminism.
Basic common sense notions of time, of space, and of what it means to be rigid and solid and insurmountable are all in some way compromised or modified or extended or enriched by the ideas of modern physics.
Before the 60s, we just thought about elementary particles as being protons and neutrons with electrons whizzing around them. And the protons and the neutrons were the smallest known particles, and they seem to be elementary.
But it became much
mysterious new particles bombarding the Earth from outer space. They had discovered cosmic rays, and they rushed to study them. By the late 1930s, they came to the conclusion that the experimental results could not be explained using the then known fundamental particles. By the mid-1960s, over 80 apparently fundamental particles have been discovered.
New fundamental particles called quarks were predicted.
There are only 12 fundamental particles arranged into 3 families. You only need 4, the up and the down quark, the electron and the electron neutrino, to describe everything in the world around us. The other 2 families are identical in every way to the first, except that they're heavier. But why they're there, nobody knows.
This is a beautiful theory. It's self-consistent, it's predictive, but it's incomplete. There's one last missing piece of this puzzle. That's the Higgs boson. We have predicted this particle since over 40 years, and now the LHC, which is already running, taking data, will find this particle if it exists.
And to find out, we're going to recreate the conditions that were present at the start of the universe, less than a billionth of a second after the Big Bang. How do we recreate those extreme conditions here on Earth? The Large Hadron Collider, 27 kilometers in circumference and filled with over 2,000 superconducting magnets, each at 1.9 Kelvin. That means that they're colder than the space between the stars. Inside here, we accelerate protons to 99.999999% the speed of light before bringing them into collision inside 4 giant detectors.
What appears to us as empty space, in particular, is in reality a wildly dynamical medium. That's what the particles we observe are. We disturb this medium in different ways. It's really the medium that's the powerful thing. This is our deepest understanding of the nature of the particles we're built out of. The particles we actually see are in fact small perturbations on this ferment going on all the time.
How do you get from elementary particles, each of which is absolutely identical to all the others of its type, anywhere in the universe, a thing that has no individuality, to the richly diverse and individual complex entities that we see around us and which we are ourselves?